Okay, next topic. Finding sectors of a circle, specifically the area of a sector, or the area of a segment of a circle, or the length of an arc of the circle. First of all, we need a couple of definitions. Sector of a circle is the region bounded by two radii and an arc of the circle. So we have two diagrams here. The circle on the left, we have segment OA and segment OB, and minor arc AB bound the shaded region. So that shaded region is called a sector. And in the diagram on the right, we have a major arc and two radii of the circle. Radii are OA and OC, and arc ABC is an arc of the circle. It happens to be a major arc in this case. The blue shaded region is again a sector of the circle. Next definition. A segment of a circle is the region bounded by a chord and an arc of the circle. So the green shaded region here is a segment of the circle because we have a chord, segment AB, and a minor arc, arc AB, and inside of that we have the shaded region representing a segment of the circle. And the length of an arc is a fractional part of the circumference. So if you think of it as a spool of, say, string or thread, if we went all the way around from point A all the way around back to point A, that would be the circumference. But we only want to go part of the way. We only want to go from A to point B and stop. So we want to figure out how long that piece of thread is if you could straighten it out. So it's a fractional part of the circumference. So the fraction is measured in terms of the degrees of the arc, n over 360. So it's that fraction of what times the circumference, which will give you the length of the arc. And we'll see how all this works out on a few problems. First problem, find the area of the shaded sector. So the area of a sector is a fractional part, n over 360, where n represents the number of degrees in the arc, divided by 360. So in this case that's 60 over 360, which reduces to equal 1 over 6. So it's a fractional part of the area of the circle. The area of the circle equals pi times the radius squared, 100 pi. So it's 1/6 of 100 pi. 2 goes into 6 3 times, 2 goes into 150 times. It's 50 thirds pi, or 50 pi over 3. Next question. Find the area of the shaded sector. Well, if the angle is 90 degrees, that means this arc over here is 90 degrees, and 360 minus 90 gives you the major arc, which is the arc that bounds this sector. That has to be equal to 270. So n over 360 in this case is 270 over 360, which reduces to equal 3/4. So now the area of the circle is pi times the radius squared, 16 pi. So therefore we want 3/4 of means times 16 pi. 4 goes into 4 once, 4 goes into 16 4 times, 3 times 4, 12 pi is the area of that sector. To find the length of an arc, okay, we're picturing this as a piece of string going around a circle. if we were to straighten the string out, how long would the length of string from A to B be equal to? So again, it's a fractional part, the number of degrees in the arc, divided by 360. 72 over 360 reduces to equal 1/5. So we want 1/5 of the circumference. So we have to find the circumference. The circumference equals 2 times pi times the radius. The radius is given as equaling 20. 2 times 20 is 40, so we get the circumference equals 40 pi. But we only want 1/5 of, meaning times the circumference. 5 goes into 5 once, into 40 8 times. We get 8 pi is the length of the arc from A to B. Two more problems. Two problems that you might see on tests similar to the SATs or the SATs itself. Find the area of the shaded portion of the circle. Well, what I'd like to do here is to say it's the area of the circle minus the area of the square. And it doesn't matter which one you start with. It says the distance from A to B is equal to 6. So if AB is equal to 6, let's find the area of the square. The area of the square equals length times width, which is 36. So we're going to be subtracting 36 from something. The area of the circle. Well, if that segment AB is 6, let's just draw the diagram again. Yeah. We'll add a page below, and we'll draw the diagram again. We have a circle, and inside the circle we have a square. If each side of the square is equal to 6, then if we draw the diagonal of the square, which is the diameter of the circle, that's a 45, 45, 90 triangle, and the hypotenuse, which is 6 times square root of 2. But that's the diameter of the circle. So therefore the radius is equal to half of that, 3 times square root of 2. So if 3 times square root of 2 is the radius, area of the circle equals pi times the radius, 3 square roots of 2 squared. 3 times 3 is 9, square root of 2 times square root of 2 is 2, 9 times 2, that's equal to 18. Or you can even take out a calculator and go 3 times square root of 2 times 3 times square root of 2, and you get exactly 18. 18 pi, however, is the area of the circle. So now we go back here and we say the area of the circle is 18 pi minus 36, which was the area of the square, gives you the answer to the question. The shaded segments, 4 equal segments, equals 18 pi minus 36. And one more problem. We have find the area of the shaded portion of the square. So the shaded portion of the square is equal to the area of the square minus the area of the circle. AB is equal to 6. So therefore AD is equal to 6. Base times height, 36, is the area of the square, 6 times 6, minus the area of the circle. Well, let's draw the diagram again down below. We have a circle, and the square going around it has segments of length 6, tangent on each side. So if this segment is 6, the segment between the 2 points of tangency here has to be the same as the top of the square or the bottom of the square. That's also equal to 6. But as far as the circle is concerned, that's simply a diameter. So if the diameter is 6, the radius is equal to 3. The area of the circle equals pi times the radius squared. 9 pi is the area of that circle. 9 pi is the area of the circle. 36 minus 9 pi is the answer to the question. Hopefully that helps. Have a good day.